Welcome everyone to our course C-based VLSI design. In today's class, we are going to show the demo of one high level synthesis tool, Vivado HLS. So, the Vivado HLS tool is available in the AMD website. It is provided by the AMD. The latest version of the tool called VTIS. So, demo I am going to show with Vivado HLS, but the same steps will work for VTIS as well. So, in this course, we have already learned what is high level synthesis. We have learned the theory. We have also seen the internal algorithms that high level synthesis tool use for scheduling, allocation, binding. Then we have also seen different kind of optimization like pipelining, unrolling and their impact in the generated hardware. In today's demo, what I am going to do, I am going to take this Vivado HLS synthesis tool and I will show how to you generate Verilog through this tool from a given C code, right. So, in this module, if you covered, you will able to understand the high level synthesis flow again. You will understand the generated Verilog, the steps of high level synthesis in Vivado HLS, right, and how to verify and validate the Verilog when you generate it through Vivado HLS. So, let us go ahead. We have already understand the importance of high level synthesis. So, we do not need to emphasize again why do you need high level synthesis. To download this tool, you should visit this Xilinx website. Xilinx is basically now part of AMD. This Vivado HLS website. The first link that I have given in this here, that will give you the latest version of the Vivado HLS, which is called VTIS. The second link that I have given, it will give you the 2018 version. Okay. So, you can download the latest version because it may have more features. So, it will the download side is bit high. So, you just download it. It has both support for Windows as well as Linux. So, based on your operating system version, you download your version. Okay. So, once you download it, then you install, you just the steps is very obvious, you just click on that and it will install in your machine. So, these are the kind of window you are going to see when you try to install. So, you just do next and all those things, you do not need to do much. So, you should select here the Vivado design edition, the first one, right. System edition is much more it will do also the I think the logic synthesis part. So, you do not need to do the entire thing just to do high level synthesis, okay. But based on your requirement, you can also do the other one also. So, once it is installed, it is done. Then once you open this, when you install it, you will see this kind of one button here or the logo, which is basically the corresponding to the Vivado HLS, okay. If you double click it, the tool will open, right. So, if you open the tool, you will see a interface like this. So, this basically called Vivado HLS and you can create project, open project and all those things, right. So, I will go ahead. Once you open it, it will ask for license, okay. So, if your institute has the license, you have to specify the license path here. If you do not have, I think it gave a student edition which is free. You can cross check the Xilinx website about the licensing part, but for student use it is free, you can use it freely, okay. So, then it will show that what are the license supports and all and then you are done, right. So, your tool is installed, you have opened it, now you can use it for your purpose, right. So, now for using the tool, what you need effectively, you have this you have to create. So, you have some design, right. So, that means you have some C code corresponding to the design in your mind. So, you will create the C file first, right. So, in our case, I will show the demo with my matrix multiplication. So, I have already written the code. So, I will show you the code what I have written. So, I have written the matrix multiplication code. So, I will open it. Everybody know what is matrix multiplication, right. So, you have given two matrices and you will multiply and then you will get the result in another matrix, right. So, in my case, I have the matrix A and matrix B and the result will be in the result, right. And all this size of the matrix is defined in this header file, right. The header file is also here with me. Okay. So, I just try to show that you may have multiple file, you can take all the file together, right. So, for my case it is a 3 cross 3 matrix, but you can actually change this value and it will work for other matrices also, right. And then here I just declare this matrix type, and this is how I have defined in high level, and this is your basically the matrix multiplication code, which is everybody knows that. If you do not know, you please cross check what is how matrix multiplication happen. So, it is basically if you take 2 matrices, it will take one row of the matrix A and multiply the column of first column, and then it will get the first element, right. To show you this, I can show you here. So, effectively if you have 2 matrices, right. So, it will take one row and it will take the first column, right. It will multiply element wise, this with this, this with this, this with this, and so on, and this will result in the only the first element, right, of the resultant matrix. This is A, this is B, this is C. Then it will take the row 1 and then column and multiply element wise, and it will give the next element, right. This is say C1, C0, 0, this is C01, and so on. So, this way then it will take the next row and again multiply the column 1, it will get this element, then this with the column 2, it will get this element, and so on. So, this is how this matrix multiplication is happening, and if you see the code, it is basically this is the code, right. So, you have this is for each row, for each column you are multiplying the elements, right. So, you have basically A I k into B k j, that value will give you A I j, right. So, it start with 0 0. So, that means 0 0, a result 0 0 will be summation of 0 1, 0 2, 0 3, the row 1, the first row of a matrix, and this is the column j 0 0, 1 0, and then 2 0. So, this is basically the column of B, right. So, if you take the first row of A, first column of B, it will multiply and it will give you the first element 0 0 element, and this is how it is happening. So, that is the function you want to synthesize into hardware. So, that means you want to get a Verilog that will do this matrix multiplication for you. Okay. And now, to verify whether your matrix multiplication code is correct or not, you need a test bench. So, as I mentioned in the video other lectures, that you should have the main function which is your test bench, right. So, I have written the test bench also here. So, this is the main function which is effectively going to call your matrix multiplication, right, which whatever the function I have shown you earlier. So, to test, what you will do, effectively you will take some matrices and will multiply with this function, and you will see whether the result matches with the actual correct results, right. So, for this test case I have only taken one scenario, but you can check for 5, 10 different matrix multiplication as well. So, here my A is this, it has these values, B has these values, and then this is the correct results. Okay. So, if you multiply yourself, you will see that the result will be this. So, what I have done, effectively I have called this function. If you remember, the function name was matrix mul, right. So, I am calling this function from here with A and B, and the result I am storing in a very in an array called hardware results. I will talk about why it is I am giving name hardware results. You can give any name, by the way, right. And correct result or the golden results I have stored in software results. Then you have to just compare whatever this result you obtain from this function is matching with these values or not, right. That is what I am doing here. If this result matches with my golden results, then it is fine. If it is not matching, then I see I found on one error, right. So, one value is not calculated correctly. So, and if this is going on and error count is I am doing plus plus, if there is no error, right. So, once it is done, if the error count is 0, that means your test passes. If error count is greater than or equal to 1, that means there are some error, and it will say how many error you have, right. So, this is how we are going to write the test bench. So, test bench is effectively take the data, call the function that you are going to synthesize, and then it will compare with the golden results, right. This is how you will write your test bench. So, this is what I have done. Now, once you have this, what will you do? You have this project, you will create a new project. Okay. So, everything is done, you have written your function to be synthesized, your test bench, everything is ready. Now, you can go, you can give some name. So, let me give the name maybe matrix some name, and you have to give that location where the files are, right. So, I will open that location where my files are. It was inside the demo folder and this, right. So, this is my folder on which those code are written, right, and I have given the project name is matrix demo. Then what you have to do? You have to tell what is your top function name. If there is only one function, even if you do not mention, this is fine, but there may be a big C code where there may be 100 of functions, right. Then you have to specify which is your top function name. So, better to give this, right. So, if you remember the function name was matrix mul. So, I will copy that function name, right. So, whatever the function name, I am going to copy that. So, that is my top level function. If there are multiple function, a tool will not understand what is your top level. So, now you have to tell what are the C files you want to add. Okay. You may not, you need not to have write everything in one file, you can have 20 files, you can add all of them, right. So, you just basically do add files, and this is my C code where the C file where the code is written, and this is my header file. So, I have to add both because header file is also needed. Then you have to specify what is your test bench, right, where you have written the test bench. So, I have already written the test bench, which is this file underscore test. So, I have added that. Okay. So, that means I have added the file to be synthesized, the file to be used for testing. You can again have multiple function. Then you have to give some solution name. So, by default it is solution 1, it is fine. Then you have to specify what is your target clock period, it is by default nanosecond. Okay. So, I am just assuming that it is 10 nanosecond. The design that we are going to generate should have clock period is at least 10 nanosecond. You can also specify certain uncertainty value, but by default you can just keep it blank. But then you have to select which FPGA board you want to use, right. So, based on your license, it will show the board you have available. So, for our license in our institute, these are the board available, and these boards there are so many lists, but if you effectively see, these are different FPGA board, right, and it will show what is the maximum speed you can achieve, how many LUTs are there, how many flip flops are there. It basically their size, you can see this is a bigger board, right, so many flip flops, so many DSPs, but these are, if you go down, there are smaller board as well, right. So, it depends on your license and all, it will show some boards. So, you can pick, because it is a small code, it does not matter. So, you have to pick a board which is good enough to take your entire design, right. If your design is very big, right, for example, if you are taking a machine learning model which is a very big Verilog code, right. So, dump it, you need probably more resources. So, based on the target you need, you pick your model, right, the board. So, that means you are already decided which board you are going to use. Okay. What what will happen if you take a smaller board and you need more, say for example, the board I am selecting, it has 100 DSP, but when I synthesize I am seeing that I need 200 DSP. So, it will say that the board you are selected, it will not work for you. So, you have to take a bigger board, right. But for this kind of project and small project, it does not matter, right. So, then if you say finish, it will create the project for you internally, right. It will take few times. The progress you can see in this bar here, it is saying some done. So, it has created the project interface, you will see this interface for you. Here you will see all the source file you have added, right. So, matrix mult, and then test bench, everything it will show, and you can open this and you can actually update there here also. So, you can change the code here also, right. So, because you have you just open that file, it is basically the same file, you can update here also, right. This is my matrix multiplication code and this is the header file. You can also see the test bench also, right. So, whatever I have shown you earlier, this is the same thing. Okay. So, that means you have created the project, and whatever things will be generated, that will come under the solution 1 folder, because that is what we have created. Okay. So, first thing is what? So, we have to make sure that this matrix multiplication code is correct, right. So, how do we check that? I have to run the C simulation, right. What do you mean by C simulation? C simulation, what will do, it will basically take your test bench file, this file, it will run this file, and which is effectively call your this function, right, because I am calling this function from here. And then if I run it, it will finally compare the values, right, and if there is some mistake in my matrix multiplication code, the test will not pass, right, and if it is there is no mistake, the test will pass. That means my C function is correct, right. So, that is done by, if you see here, lot of buttons are here. So, this button, if you see, this is run C simulation, it basically check your whether your C function you have written correctly or not. So, if you click it, there will be some, this window will open, you can actually clean build, that means you will start from scratch, or you can work on that. You can also have some command line argument, for my case it is not there. So, if you do click, you should see this window if something is going correctly or not, right. So, here you will see that lot of information is coming, and you should be aware of what is coming here. Okay. So, you see here that it basically saying that I am running the this Vivado HLS tool, and then I am taking this from this demo, and this is my target devices, whatever you have selected. Then I run with GCC compiler. So, by default this Vivado HLS use GCC compiler, and it is basically running your C file, the test file, nothing else, and it is basically saying that test pass. This message comes from here, it does not come by default, right. Whatever I written here, that means there is no error, right. If there is some error, it will not pass. Say for example, if I change one of the value here, let us say I just make it 5, right. So, that means so this is basically my, I mean just try to show that something is not matching. So, your so you change it, and then if you run the C simulation again, you will say that there will be one error now, right. So, if you start C here, starting your C simulation, the same thing is going on, and finally it says there is some error, right. It says basically, so there is one mismatch detected, because I change one value just to show the impact, right. So, that is why it is basically identify that, and it basically say that it is not correct, right. So, this is how you will basically you will see that if something is wrong in your code, for example, instead of do that, so suppose in my code also I change something, say if I make it plus, so everything this code is not correct now, right. So, if I now do the C simulation, all of them will fail, it will say 9 mismatch, because whatever you are calculating is wrong now, right. None of the matrix value will be correct when I in the resultant matrix, right. So, I am doing it. Okay, sorry, I probably pressed the Verilog one. So, I just sorry, instead of this I will show you that step next. So, if I do the C simulation, it will do the C simulation, but your code is wrong now, right. So, because you change the code such that, so it will show now there are 9 mismatches, because all matrix value will be wrong now, right. So, that this command is coming from your test bench only, right. So, in the test bench only you have written that error, this many mismatches are there, right. So, if your code is not correct or something is wrong with your golden test bench, you will see, you will be able to detect that. So, you have to make sure that you are taking the right version to synthesis. Okay. So, this is done, means your C code is correct. Now, you have to do the C synthesis, right. That is, this is the C synthesis button. This is basically will convert your matrix mul function into the RTL. It will not change your this test bench. Test bench is just to test your C file, right. It is not going to be synthesized. Synthesize will be this, the top function that I mentioned earlier, right. So, now if I just click this C synthesis, now C synthesis will work, and you should closely monitor what kind of comment is coming here. So, it is it say that Vivado HLS is running, I am taking this project, then I am checking design, analyzing the design, is there any synthesis directives, okay. Then I will go through the comment. This is very important to see what are the things coming here, okay. So, effectively you will see that it basically add all the files, right. These are the 2 files you mentioned, both have come. Then it just see is there any optimization directive you have given for this case I have not given anything, then it just checking the pragmas, there is no pragma for my case, then it converting the code. So, we try to apply the C level optimizations and then it just check whether your code is synthesizable or not, right. So, as I mentioned in some classes that for example, dynamic memory allocation like malloc, function pointer, those things are not synthesizable, right. If your code has those things, it will basically give a error in this line that your code is not synthesizable, right. So, then it if you have something, it will unroll the loop, okay. Probably I have that comment. So, this test bench I can now remove, okay. I will just remove this pragma. So, for example, the baseline I am going to synthesize, I will not have anything, okay. So, it will basically whatever. So, I have used this pragma HLS unroll. So, that is why doing the unrolling, right, otherwise it will not do, okay. So, whatever the pragma you will do, it will apply your code. So, now your code is ready for synthesis, right, and then it will do the architecture synthesis, which is HLS, right, starting hardware synthesis, synthesizing matrix multiplication, then it is doing the scheduling, right. So, we have taught you the first step is scheduling, the other previous part was the pre-processing, right. Now, it is doing the scheduling is done, then it is generating this micro architecture, which is the data path allocation and binding, then it is doing the variable lifetime analysis, which is the register allocation and binding, and then exploring the resource sharing, which is this ALU allocation and binding, right, and then it is basically the binding. So, it identify allocates and then it binds, right, and then this data path is generated. Now, it is generating the Verilog code, right. So, all the steps that we have talked about in the theory, same steps is being followed here, right, and then it create the port and all. I will talk about that, what port it is creating and why it is creating, and then finally, it is finishing the results, okay. So, it takes 17 seconds to do that. So, I will first create the version where there is no optimization, right. So, I comment out all the optimization I want to use. So, synthesis is going on, then what is going to be generated, I will show you. Synthesis is done. So, then once you the synthesis synthesis is over, it is going on, yeah, it is done actually, okay. So, then you have to see what is getting generated. Now, if you click on this solution folder, you will see the scene folder, in which you will see the report. It also generates Verilog, VHDL and system C. So, we will mostly look into this Verilog. So, you will see this is the file is getting generated from that, okay. We will look into that, and then this is the simulation report. You can open the simulation report and see what kind of reports come, but most important thing, you should see the synthesis report, okay, which is basically this opened here already, okay. So, you will see that all the resource usage. So, your target clock was 10 nanosecond, you are able to generate a Verilog which has 4.5 nanoseconds. So, is able to meet your target clock, right. Then you will get the latency. Latency is the number of clock cycle you need to complete the execution, right. So, here it is mean and max, there are two kind of values coming, I will explain why. It is kind of 79 clock second clock period, right, or 79 cycles, right. There are, if your loop has a fixed bound, there is no variable. If you take this path, it will take 10 cycle, it can happen, right. There is if else branch, right. If has 20 instruction and else has 1 instruction. So, obviously, if you come through if branch, it may need 10 cycle to schedule that, and else branch maybe need 1 cycle. So, then it may varies, right. Or if you have a loop which has bound is not fixed, it depends on your input size, then in one case it may be more and in some cases less, right. So, specifically in the control flow, that will give you the mean and max. For variable loop bound, it will not able to calculate, it will show some question mark here, because it will not able to calculate, it depends on your input, right. So, it will not give you any value. So, this is the latency. So, it is taking 79 clock cycle to execute, although your code looks only 3 lines. I will explain why it is that, okay. If you see here, your each row is basically you have 3 cross 3 cross 3, because I have taken 3 matrix. So, there are 27 times this operation is going to happen, right, and this operation has a multiplication, array read, array write plus a addition. So, it is although it is a single line, there are 2 array read, 1 multiplication, 1 addition and 1 array write. So, all those 3 is basically taking 3 cycles somehow, right. So, 3 into 27 is 81, and it basically somehow adjust for maybe for some cycle. So, that is why the value is coming somewhere is 79, okay. And the interval is the initiation interval, the I talked about in pipelining explanation. It means that once you start this, you have to wait for 79 cycle. Once the result is done, then only you can give the next matrix, okay. That so is basically it's same as the latency. But if you apply pipeline pragma at the start in the loop itself, then your II could have been much low. You can give the matrix maybe in after 10 cycle or not, okay. So, this is how you have to understand the latency interval, okay. Then the resource usage. So, in a FPGA block you have DSP, which is the multiplication. So, you have a multiplication here. So, it is using a DSP, okay. So, because I have not unrolled or anything. So, every iteration is going to happen one multiplication. So, at most one DSP is needed, right. Then there is no FIFO and all. You have registers. So, 44 flip flop has been used to store the values, internal values, right. And then you also have the LUTs or SLR, which is basically you have 6 lakhs in the board you have selected. It only uses total 185 for this addition, multiplexing and all those things, right. So, it effectively use 1 DSP, 44 flip flop and 185 LUTs. This is a baseline implementation, okay. So, this is how we can actually see the kind of resource utilization, okay. It is much lower than the available. So, you should not be worried about, okay. So, this is what you should understand, and if it is not, you have to apply. So, suppose your resource is more than of the availability, then you have to apply different optimization which should reduce the area, okay. If your clock is not meeting the target clock, then you have to apply certain technique which will improve the clock period, right. If your initiation interval is too high, you have to apply pipelining kind of pragma to improve this initiation interval. So, all those things you will be able to do, okay. So, once you do this, this is basically so your results are good, right, because it is meet target clock, resource utilization is not high, probably your latency is bit high. So, you should apply certain thing to improve the latency, okay. So, next things you should do is the analysis. The button in the top right control, this analysis. In the analysis, what it will show, I will show you probably it has 4 clock steps, right, in your controller FSM C0, C1, C2, C3, C5, and this is the kind of loop. So, the first clock is this, and it will effectively show you in the scheduling, right, in which step which operation is being done, right. For example, this I plus plus is happening in C1, then this multiplication will be happening here. This is the multiplication thing, it is happening in the C4 step, and it is going to loop, right. You can understand this is a matrix multiplication is a loop, right. So, this C1, C2, C3, C4 is going to repeat, right. So, this is I loop, you are incrementing the I here, incrementing the j here, and this is the kth loop while you are doing the multiplication, right, and this C3, C4 will repeat. Once this is done, you will go back to this jth loop, and then once the jth loop is done, you will go back to the ith loop and you will increment I, you come to j again and so on. This is how the code will execute. But important thing here, you can actually see how the scheduling happen by the HLS, right. So, this is good. The another important thing here, that if you click on that, you can see, so this is the 3 address code, right. I have told you that your actual C code will be converted into IR, intermediate representation, right. So, that 3 address code will be used. So, that is why it is coming like this. But if you want to see which line is corresponding to this, if you click on add to source, it will show the source here, the C file that I have written, and it is basically corresponding to this line. So, this whatever the 3 address code here, this is nothing but corresponding to this, right. So, if you click on this, go to source, it will effectively show you the line. It is basically corresponding to the column that a j. So, it is basically incrementing the j, right. So, all the j plus plus things you are doing, this 3 address code is corresponding to that. So, this way you will able to correlate the operation that is happening in which clock versus the corresponding C code. You can also check the corresponding Verilog, right, VHDL also. So, it will open the Verilog and it will say that this is basically nothing but this wire. Okay. So, this way it will actually connect both, right. So, if you click on this to this Verilog, it will show you this MAC. It is basically it is the multiplication, right. So, if I show this, it is the multiplication, this star is multiplication, it is effectively this this line, right. So, this matrix multiplication block. So, this way you will able to analyze the actual scheduling is happening, corresponding registers or the ALU that is being used in the Verilog, and what is this 3 address line corresponding to the source code. So, everything is possible through this analysis, and you should always, if you want to understand how the scheduling happening, you must do this kind of thing. Okay. It also have a lot of information, like it will actually show that how many clock your that row, there are matrix row call and all, right. So, this call is iteration latency 8. So, every 8 clock it will this your jth block is happening, right. ith block is happening after every 26 clock cycle, and the top level function is 80 because 79 was the iteration interval, right. So, this is how you will able to see that each loop how much time is taking, right. So, this is you should actually understand these things well, so that you will exactly understand how your C code actually mapped into the corresponding Verilog or in the hardware. Okay. So, this is very important steps, and then once you are happy with this, you should also see what is the Verilog generated, right. So, I will open the Verilog. So, it has generated 2 files, I will open both and I will show you what is them, right. So, this is basically MAC. MAC is basically DSP, multiply and accumulate. So, this is one of the DSP 48 instances, and you can see that effectively all this code is matrix mul. This is the module name, this is the definition, and finally, it is instantiate one DSP block. So, effectively this is the multiplication call, nothing else. This code is just the multiplication. The major file is this one, and we must understand this code very well. This is corresponding to this C code that we have written, right. So, the code we have written is this matrix multiplication, this is the my C code, and this is the corresponding Verilog code. Okay. If you remember, see here your C code has argument is ABC 3 arrays. Okay. But when you see here the interface has something else, it is not array, right. So, you should understand why this has been happened, right. So, let me explain that. So, what you have done, you basically have this matrix multiplication, matrix, you are sending arrays, right, array A and array B, and result is in result array, right. So, this was your C interface, but in hardware when you generate this, so this is the module corresponding to matrix mult, right. But where is your arrays A, B and C? So, the high level synthesis tool assume that since this is a 2-dimensional matrix, it is kind of a memory, it will be mapped to some memory, and then memory is outside because this is the interface, right, because they are not inside this matrix multiplication hardware, because you have passing them, right. So, that means this A, B and result is somewhere else, it is not the Verilog that you have generated. So, it will assume that there is some memory outside which name is A, there is one memory which name is B, and there is one memory which name is result. Okay. But how do you access memory? You need address, right, you need address, you need the address, you need a data line, so that the data either goes through this direction, you can read or write, there will be some enable, read enable, write enable, right, whether you want to read or write. So, these are the signals you need, right. So, for each such memory, it will effectively create this many, right. There will be one address, there will be maybe read address, write address can be different also, there will be data, write enable, read enable, all those things will be created for each of this memory. And whenever you want to read the data, it will basically give the address which value you want to read, the corresponding read enable equal to 1. So, that the corresponding value will come through this data port into the module, right. So, this is how the interface is going to be created, and that is exactly being done. In addition to that, once you create this module, you probably plug in into a bigger design. So, you need certain synchronization signal, right. So, that means there is something called AP start. It will expect that you will say that you start this block, right. Until you give this AP start, it will not start the execution, it will wait, right. Once this is done, it will create kind of done signal. That means the result I have created, this is now ready. You can actually give me the next one, right. So, this kind of handshaking signal is needed, because once you plug this matrix multiplication in a bigger module, you have to say that, oh, matrix multiplication going on, I cannot take this data. Once this done is 1, I can take this data and do something else, or whenever this done is 1, I can give the next data, I can store the entire data in this module, and then I will say AP start, because if the matrix size is big, you cannot store everything in one clock, right. So, you may have to give say 100 clock to store the data in AB, and then you will say AP start, oh, you can now start the next matrix multiplication, right. This is how the interface is going to be created. So, so this is actually been done, and now if you see this code, if you see here that it has this kind of synchronization signal, this is the clock, this is the reset, it is always there. AP start is the start signal, until this is 1, it will not start doing it, right. It has AP done, that means I have completed my execution, and there are other synchronization signal like ideal ready, right. Now, that is what I am talking about. For each A, it has generated address, read enable, this is the data, and similarly for this is read enable or write enable, and then you have this is read enable, because you are reading from A only, you are not writing anything to A, right. So, it is read enable. Similarly, for B also it is creating address, read enable, and the data line. For the result you are writing, right. So, you basically doing this address, write enable, the data, it also has read enable, because you probably have to read the data if needed, right. So, this is the interface it will create. It will not create a port only for one port for A, one port for B, one port for C. It will create this many ports. Okay. This is important to understand. Now, let us understand, I talked about the clocks. So, we first see the controller FSM. So, this is the controller FSM, right. What is happening here? So, this is the controller FSM till this point. It has 5 states. I told you that C1, C2, C5, the state 1 is C1, state 2, state 3, state 4 and state 5. So, C1, C2, C3, C5 is this, C5 is state 5, right. You can see that in the state 1, until you give AP start, it will just remain in AP start. Okay. So, that means it will not start doing anything. So, it is just ideal state, and then once you give AP start, it will go to state 2 and you start the loop, right. You go to state 2, and then if it is state 2, it will go to state 3, right. So, once the exit condition is true, that means your loop is done, then it will go to state 1, that means your execution is completed. Now, I can start the new one. Okay. This exit condition is the when your I number of iteration corresponding to I is done, right. Otherwise, you go to state 3. State 3 is the jth loop, right. So, here you will see the for the jth loop exit condition, if it is done, then I will go to the state 2, that means now I will make I plus plus, right. Otherwise, I will go to state 4, which is my internal loop, right. So, in the state 4, the kth loop, right. If the kth loop is done, I will go back to state 3, then I will increment j, right. So, from this I will go back to this state. Otherwise, I will go to state 5, and that is where I am going to do this. This is the loop, right. State from state 5, I will do this all this operation of multiplication and add, and I will go back, right. So, I will go to state 5. So, this is how the overall condition is going on, right. So, if I explain the code, so effectively the execution is exactly the way your C code will done. So, So, this is your C1 or state 1, and then this is until you give the AP start, it will remain there, then you will come here, this is your C2 or state 2, then it will go to C3, then C4 and C5. From C5 it will come here. Whenever the condition is done, right, this is k greater than of the limit, it will come here, right, not equal to the limit whatever the value, it will come here, otherwise it will go inside, right, and then once it is done it will come back to this, once this is done it will come back to this, right. So, this is how the nested for loop will going to execute. Okay. Okay. So, we understand this controller exactly what it's implement the Verilog. Now, look into the code, what is the data path and all. So, these are the data path operation. Okay. So, these are the combinational operation which is done by assign statement, but exactly which operation is happening in which state is controlled by the control signal that I talked about. Here control signal is given in a nice way. It is basically saying that if it is a state 4, you make your C equal to 1. So, this is the control signal. The control signal is controlled by the control state name itself, right. Most interesting state is 5, because in 5 only the operations are happening. So, let me see what are the operations happening in state 5. You can see that so these are the operation for each state, right. So, for example, if it is state, if your state 3, this is basically you can see I is there, right. So, this is the register corresponding to I. You will update register I. How? If you search this one, this value, you will see that this value is nothing but this value, right, which is basically if I search this now, this will be some I plus plus, I will show you. So, this is basically I plus 1, right. So, effectively in state 3, whenever I am in state 3, I am doing I equal to I plus 1, right, that is exactly it means. Okay. So, this is what is happening in state 5, and similarly if it is update. So, for every state the corresponding updation is happening. So, these are all the registers, right. This is corresponding to state 2, then this is state 2, this is state 1. So, these are the operation is happening in each state. Okay. So, I will see the state 5. So, yes, state 5 I was looking for. So, here actually this register is getting updated. If you search this, you will see that this is updating by this. So, let me see, this is that the k plus plus, right. So, this is how every control state it is which operation will be executed, which register transfer level operation will be executed, that is determined by the state name, and this is the control signal effectively. Whenever this value is 1, that means this operation will be executed, and this is the register name, and this is the wire, and this is updating here. The wire will update every clock, right. So, this is how the entire behavior is getting executed. Okay. So, once you are done with understanding this Verilog, we also have to make sure that this Verilog is generated by HLS is correct. Okay. There may be some bug in the HLS tool, and as a result the code may be wrong, right. How do you check that? You have this, the run CRTL co-simulation. This basically say that you will run the Verilog with the same test bench you have written for C. So, it will take the same interface, convert that test bench into a equivalent interface corresponding to the Verilog. So, what is going to happen here in this test bench? So, wherever this matrix mals was calling for C, now this matrix mal will be nothing but this Verilog matrix mals. Okay. So, it will basically replace that with this module, that is all, right. So, this is what internally going to happen. So, now the result will come from this Verilog code, not from the C code. Okay. So, if I run this, so because I have did some changes, I mean whenever I was going through, maybe somewhere it gets changed. So, you can actually say okay. So, you can synthesize the Verilog or VHDL. I am mostly looking into Verilog. If you say yes, so now this you should see the window what is happening. it is basically saying instrumenting C test bench. This is what I talked about. It will take the same test bench, it will do something internally, so that the same test bench can be used for Verilog simulation, right. This is what is going to happen here. Okay. So, this is the RTL simulation is bit slower, right. So, it is taking little bit more time. So, effectively you see the similar kind of message is coming, and it is basically do the some elaboration on all those things, and then it creates the simulation is going on, right. So, you will see this green means something is going on inside. Now, this is done, right. So, it basically said test pass, the same message is coming, that means your Verilog is correct, but you can see here that overall run time is somewhere it show the overall run time. You will see that run time is much higher than the C simulation, okay. But thing is that your overall co-simulation passes means your generated Verilog code is correct, okay. So, that is all for the demo 1, where we have shown you that how do you create the test bench, how do you do the C simulation, how do you run the Vivado HLS to generate the Verilog, how to understand the results in terms of the area, the resource, latency, initiation interval. We have also explained how do you analyze your generated code, how the schedule happen, which operation is mapped to which Verilog code, right. All this correlation you can do through analysis, and then you should also see the generated Verilog. You have seen that how the controller FSM is working and how the Verilog will looks like, right. So, this is what, and also important thing is the interface. So, interface is not just like your arrays, rather the ports, okay. So, this is so completes the demo 1. Thank you.